today we're looking at geometric sequences. So you guys have looked at sequences before. They're a list of numbers, a list of terms. And then sometimes we can find a distinct pattern in this list that helps us write a rule for this. So with our arithmetic sequences, to get from term to term, we saw that there was a common difference, something that you added or subtracted from each term to get to the next. With our geometric sequence, there is a common ratio, something that is multiplied or divided, but we usually write it in the form of multiplication, to each term to get to the next. So you'll notice in the example up here that's a little bit generic. It has all the variables in it and stuff like that. A is the first. Okay. Notice the next term is A times R. And then A times R squared, because that would be like A times R times another R. And so they're multiplying R, which is what we're going to use to represent the common ratio, times each term to get the next. Okay? Some of the vocabulary here is the same. We have recursive definition. A recursive definition is telling someone how to get the next term based on the previous one. So you have to give them the first term. Otherwise, they wouldn't know where to start the list or the sequence. Then, to get the nth term, you take the n minus 1th term. Remember, that means the term before it. And you multiply it by R. The explicit definition, okay, so to get any term, and so we saw this when we were doing Finance Week stuff, and we've seen this with our arithmetic sequence. Recursive is great because we recognize the pattern. However, it's not so great if I want to find the 100th term. I don't want to know the 99th term, the 98th term, etc. to get the 100th term. I want to be able to plug in 100 as my term number and have a formula that gives me the actual term. And so for our geometric sequences, that's what this rule is going to do here. So this is going to be your explicit rule, okay, or your definition for geometric sequences. So that's going to be a formula that you're going to want to know. Okay? So the nth term can be found by taking the first term and multiplying it by the ratio to a certain power. Because you can see that all terms in this geometric sequence are multiplied by a certain power of r. The first term is times r to the 0 power. The second term has r to the first power. The third term has r to the second power. The fourth term has r to the third power. Notice they all have a power of r that's one less than their term number. That's why you see this exponent of n minus 1 on r. So let's recognize this pattern and be able to work with it a little. So up here are two sequences. We're supposed to decide if they're arithmetic, geometric, or neither. So notice in sequence A, first term is 5, next term is 10. So if I was adding to get there, I'd be adding 5. But if I add 5 to 10, I don't get 50, I get 15. So if we tried 5 times 2 would have made 10, but 10 times 2 doesn't make 50. So this does not follow an arithmetic or a geometric pattern. Therefore, it is neither of those types of sequences. Now, when I look at sequence B, I can tell it's not arithmetic because see how it goes negative, positive, negative? There's no way that I added a bunch and then added a bunch again and it turned back negative. So I can tell it's not arithmetic. So then it becomes geometric. So negative 10 times some ratio would equal 6. So then that ratio would have to be, let's see, negative 3/5. So let's check. Negative 10 when multiplied by negative 3/5, that comes out to be 6. That checks as our second term. Now if I take 6 and multiply it by negative 3/5, do I get negative 3.6? So I get negative 18 over 5. And if I divide that out, I get negative 3.6. So negative 3/5 is a common ratio for this sequence. So it is geometric. With a common ratio of negative 3/5. All right, so here is part of a geometric sequence. They tell you it's geometric in the directions. So here's what we know. Okay, we know that the first term is 2, and we know that the fourth term is 128. And then we're going to use the rule here to help us figure out what that ratio is so we can multiply it and get those missing terms in between. So of the rule, find the nth term. You take the first term and you multiply it by the ratio times n minus 1. And then here's what I know. I know my first term. So my first term is 2. So I can plug it in. I don't know my ratio, and I would really like to know my ratio. So right now, all I can really get for the generic rule is this. When we worked with arithmetic sequences, knowing another term in the sequence actually tells you two things. This is like saying when n is equal to 4, a sub n is equal to 128. And just like we did with arithmetic series or even with writing an equation of a line, that's like a point that we can temporarily plug in to solve for a missing piece that we want to know, like r. So I'm going to plug in 4 for n while I plug in 128 for an. So I'm going to have 128 equals 2. And I'm going to solve this equation, and we should have some familiarity in solving this equation because of our last unit where we worked with radicals. Okay, so 4 is going to 4. So now I know my common ratio is 4. So when I look at this sequence, I know things are getting multiplied by 4. So 2 times 4 would be 8. 8 times 4 would be 32. And I'm just going to check if I multiplied 32 times 4, do I get 128? I do, so I feel successful and that I've completed that geometric sequence. All right, looking at a word problem example. So you work as a store manager. You need to clear some inventory, and you decide to discount each item by 30% of the previous week's price until it is sold. So the original price of one item is $60. So let's see. It would be $60 week 1. It would be 30% off, which means the person's going to pay 70% of the item. So I would choose to multiply it by 0.7. Then the next week, this would have made a new price, whatever 60 times 0.7 is, and that person's only going to pay 70% of that. And then this pattern would continue. Okay? So what I see here is I do see a geometric sequence where the first term would be 60, and the ratio, or what each term is getting multiplied by, is 0.7. Okay? So then the question says, what will be the cost of the item during the 5th week of the sale? So this is week 1, week 2, etc. Remember, your n here is like the week number. And then your AN here is like the cost that week. Okay? And we can write, since it follows the geometric sequence pattern, we can use the explicit rule to help us write a rule for this. We have both A1 and R, so we can get our rule. Our rule is going to be 60 times 0.7 to the n minus 1 power. So then when they ask me for the price the 5th week, I'm not going to figure out all the prices in between, though if you were in a bind, you could do that. I'm going to say, what is 60 times 0.7 to the 5 minus 1 power? And I'm going to go ahead and do that calculation. So that's 0.7 to the 4th power, and then that's multiplied by 60. Okay? And I basically get that A5 is this number. So in the context of the problem, I would say that that week they are charging $14.41 for this item. All right. So here's another problem where we have missing terms. So we could look at this the same way we did before. I know that for some of you, you're like, I can guess and check and figure this out, and that's great. But if they gave you terms that were much further apart, like here's the 8th term and the 100th term or something like that, you wouldn't really have that luxury. So I'm going to do it the algebraic way so you have that to fall back on if your number sense isn't there right when you look at it. So we know that the first term is 28, and the third term is 7, and they tell us it's geometric. So we're going to go back to our explicit rule and see what we know. So we know first term is 28. We really want that ratio because it's going to help us distinguish terms in between. Okay? So again, I'm going to use this, and that like when n is 3, an is 7, and I'm going to plug those in like an ordered pair. So 7 equals 28 times r to the 3 minus 1 power. So 7 equals 28 times r squared. If I divide both sides by 28, I get that r squared is equal to 1/4. So in this case, I'm going to square root both sides and get that r is equal to positive or negative 1/2. Okay? So there's actually two options here. One option is the ratio is positive 1/2. And in that case, times 1/2 is 14. And then 14 times 1/2 is 7. And this portion of the sequence would look like this. The other option is that the ratio is negative 1/2. So 28 times negative 1/2 would be negative 14. And negative 14 times negative 1/2 would be positive 7. And I would have something that looks like this. Okay, so there are two options here. If you don't know that missing piece, it could be negative, it could be positive. This is different than the previous problem because we had the fourth term rather than the third term, and that's why we didn't get both the positive and the negative option. Okay? So you guys want to know your explicit rule, how to identify a geometric sequence, and what the common ratio is.